Let's take a look at the 2015 free response AB section, questions 1, 2, and 3. In question number 1, you're going to see that we're looking at a classic in-rate, out-rate problem. Let's take a look at the words to find out how we know that. The rate at which rainwater flows into, so we already see very quickly we have an into rate. A drain pipe is modeled by the function r, where r is given as this function. And notice that r of t is a continuous trig function, and r represents the in rate of our function, or the in rate, from the hours of 0 to 8 inclusive. The pipe is partially blocked, allowing water to drain out of the other end, so there's a key word, at a rate, there's the other keyword, of d of t. So d of t is the out rate, and it's measured for 0 to 8 inclusive as well. There are 30 cubic feet of water in the pipe at t equal to 0, so we have an initial condition of 0:30 that we will likely use somewhere in the problem. In letter A, we right away see our trigger word phrase of how many, so we're going to accumulate. And we do not need the initial condition. We're just simply going to accumulate the amount of water flowing into the pipe by accumulating the area underneath the in rate. So we accumulate starting at 0, stopping at 8, and this is my in rate function. And I'm going to do that directly on the calculator. I'm going to get 1 point for my integrand, meaning I'm using r of t. And I'm going to get 1 point for my answer for the rounded or truncated answer. In letter B, is the amount of water in the pipe, and here's the heart of the problem, increasing or decreasing at time t equal to 3? Well, we know in calculus, if we want to know if a quantity is increasing or decreasing, we need to examine the sign of the derivative of that quantity, and in this case the quantity is the amount of water. Therefore the rate is the total rate, which is in this case figuring out the value of the in rate minus the out rate at t equal to 3. Well, remember they gave me the in rate and the out rate, and it is likely that you have r in y number 1, maybe not, and d in y number 2, but I think in this case, since the functions are fairly I won't say big, but they're more to type in, I probably would put them in y1 and y2, and then I'd go to the home screen and I'd tell the calculator to evaluate y1 at 3, y2 at 3, subtract, and we would get a negative output telling us that the quantity, in this case the amount of water, is decreasing. So we get 1 point for using r of 3 and d of 3, and we get 1 point for answer with correct reason. In letter C, let's go back up and figure out what they're asking us there. So in letter C, at what time on 0 to 8, so we have a closed interval, is the amount of water in the pipe at a minimum? I cannot stress to you enough how important it is that you be able to recognize EVT and that you know exactly how to write it up. EVT says the absolute max or the absolute min will occur either at a critical number or the endpoint. So we have to consider them as possibilities as to where the absolute minimum and absolute maximum occur. So we're going to set the total rate equal to 0 to find the critical numbers, and we'll let the calculator do that work for us. So the first thing we're going to do, just like I said earlier, I would have at this point have y1, I would have had r of t in y1, I would have had d of t in y number 2, I would have turned both of those off, and in y number 3 I would now define a new function r of t minus d of t by making the calculator do y1 minus y2, and y4 I would make equal to 0. Now I'm going to set those two equal to, or I'm going to figure out where those two curves intersect. Or the other way to do it, of course, would be to figure out, just use y1 and y2 and see where those two curves intersect. That would be the same thing as setting the overall rate equal to 0. It doesn't really matter. And when we do, we're going to get a value of 0, which is already one of the endpoints, and we're going to get the other critical number of 3.71658, and we're likely going to store that number into the calculator. So I want to take a look at what that function looks like, because there are two ways that we can justify this, and I want us to see the graph so we can consider that. So I'm going to bring my calculator up and let you see that there are a couple of ways to write this up. So I'm going to just cover this up for now. In y1 I have r of t, and in y2 I have d of t, and in y3 turned on I have y1 minus y2, and y4 is equal to 0. I set up my window to start at 0 and to stop at 8, since that's the window that they gave me, and I found the point of intersection right here to be exactly what they had, to be 3.271658. Now, I did not store that number in my calculator because I want to talk to you about the two ways that you can write this up. One way is to use a table of values, but that's not the way I'm going to talk about right now. In this case, you have three values. You have the endpoint 0, which they talked to us about. You have the endpoint 8, which they told us about. And we found only one critical number. Now, ladies and gentlemen, you cannot just simply justify that there's an absolute minimum at x equal to 3.272 because the first derivative or the graph of this derivative changes from negative to positive. You will not get the justification point. You've simply justified a local minimum, and we're looking for the absolute minimum. You can, however, say and record what you see, and we've done this in class before, to say from 0 to 3.272, the derivative graph, or r of t minus d of t, is less than 0. Therefore, the amount of water is decreasing. And this is the important part. Therefore, there is less water at 3.272 than there was at 0. That compares the endpoint and the critical number, and it rules out the first endpoint. Then you have to continue on to say from 3.272 to 8, the derivative graph, or r of t minus d of t, more specifically, is positive. Therefore, the amount of water in the tank or in the pipe is increasing. So, and this is the important part, there is more water at t equal to 8 than there is at t equal to 3.72. Now you have declared, and you've compared both endpoints, and they're in your conversation, that the absolute minimum occurs at x equal to 3.271. That's one way to do it because there's only one critical number. Now the other way is to simply create a table of values, and that's why you see up here they wrote an integral. You didn't have to write that integral to get the points if you did what I just said. So in this case, they wrote the integral that will accumulate the amount of water for any time t. So at 0, we already knew that there were 30, I think it's gallons, what we're measuring in. I lost my units, so I'll have to go back up in a second. And at 3.272, with the calculator, we accumulate that much water. And at 8, we accumulate that much water with the calculator. So you can put it in a table, and that table will serve as your justification with your declared answer. So that's two different ways that you could write up extreme value theorem for this particular problem. But the most important thing, I cannot stress enough, you can't just justify a local argument by saying the derivative, in this case, r of t minus d of t, changes from negative to positive. It will not get the justification point. Okay, I've pounded that enough. Letter D, moving on. The pipe can hold up to, or at most, 50 cubic feet of water before overflowing. For t is greater than 8, water continues to flow in and out of the pipe at the given rates until the pipe begins to overflow. Write but do not solve an equation involving one or more integrals, so this equation has to have an integral in it, that gives me the time w when the pipe will begin to overflow. Now remember, it begins to overflow when we have more than 50 cubic feet of water. So the key is figuring out, when do we get 50 cubic feet of water? So the equation will require you to use the initial condition. You're going to need an upper bound in your integral of W, because they say that's the time that we're looking for. There has to be a variable disagreement that we'll see below. And we're going to accumulate the in rate minus the out rate, and we're going to set that integral equal to 50 because we need an equation. So if you look down here, this is the 30 gallons. Is it gallons? I got to go back and look at that. I think it was gallons. Cubic. Oh, no, it's cubic feet. So 30 cubic feet of water. We're going to accumulate starting at 0. We don't know when we're going to overflow. So that's the W that we're looking for. And this is what I'm talking about with the variable disagreement. We're trying to solve for W. Since that's the variable we're solving for, it's the upper bound, and it will go in place if we were going to do the differentiation in place of T. And we set that equal to 50. So we get 1 point for the integral. That doesn't necessarily include the 30, but the integral would be this part right here. So if you had that, you get 1 point. And then for all of the rest of it correct, you get the 1 point for the equation. That's question number 1. Question number 2 is an area volume problem. They've given us a function g of x, they've given us a function f of x, and they've given us a graph that we can see over here. They've clearly told us that the two curves intersect at 2, 4. They have not told us this point of intersection here, so we will likely have to find that with our calculator. And they've told us this point of intersection here. Find the sum of the areas of regions R and S. So we're finding this region of area, top minus bottom, and this area of region of area, top minus bottom. So first, we're going to have to put the functions into our calculator. F of x would likely be in your, I don't know why I'm writing with a mouse. F of x would likely be in your y1, and g of x would likely be in your y2. And we're going to have to figure out where they intersect, and we're going to store that value if it's a long decimal number instead of a whole number. So when you use your calculator to find that number, you get the long decimal value of 1.032832, which should be stored in your calculator, and you're going to use that number. So when we find the area, I don't want you to write A here. I want you to write 1.033. Even though when we type it on the calculator, we're going to use A, but we're going to declare it as 1.033 on paper. 1.033. Calculator's going to do the work here, and we're going to find that sum, and that's an easy question. The area of the two regions combined is 2.004. 1 point for your limits. That means find the point of intersection. 2 points for your integrands, meaning that you have top minus bottom, and 1 point for the correct answer. In letter B, they're having us focus only on region S. So let me get rid of this, and let me get rid of this. So in region S, the base of the solid, whose cross-section perpendicular to the x-axis are squares. So we're making cake. We're slicing perpendicular to the x-axis. We start with geometry. The formula for the area of a square is a side squared. In this case, remember, there's our square. And this side right here corresponds to this distance across. We're looking at straight from above, so we can't really see the square. This is the base, or the length of the side. So the side is the top minus bottom, which in this case would be, which curve is which? So this one is the, wait, I've already got lost here. So in this region, F is on top, so there's the F, and G is on the bottom, which is this region right here. So we have the length of the side is f of x minus g of x. We're going to accumulate that by substituting the length of the side in place of s. We're going to start at this point of intersection here, which we remember we stored in our calculator, and we're going to stop at 2. All right, so with the calculator, after we set this up, so notice I'm starting again at 1.033. There's the top minus bottom, quantity squared, area of square, side squared, from to 2, and we get 1.283. And then finally in letter C, let me get rid of what I cleaned the graph off over here. All right, so in letter C, let H be the vertical distance between the graphs of F and G in region S. So actually we were just looking in that at that distance. So the vertical distance between the graph of F and the graph of G. Let H be that distance. So we just defined in the last part of the problem that H is f of x, top curve minus bottom curve, because it's the vertical distance. Find the rate at which h changes with respect to x. So in other words, they're telling us to find dh dx. We're taking the derivative with respect to x when x is equal to 1.8. So when we, as I said, our function h is f of x minus g of x. So when we take the derivative with respect to x, the derivative of h of x is h prime of x. The derivative of f of x is f prime of x, and the derivative of g is g prime of x. Notice all three functions were already in terms of x, and then we're going to substitute 1.8, and with our calculator we're going to find the derivative of those two functions at 1.8 and get our answer. Number 3, table problem. Joanna jogs along a straight path from 0 to 40 inclusive. Joanna's velocity is given by a differentiable function. Remember, differentiability implies continuity. And so since v is a continuous function, that means that the position function is differentiable, thus continuous as well. Selected values of v of t, where t is measured in minutes and v of t is measured in meters per minute, are given in the table above. In letter A, we're going to use the data in the table to estimate the value of v prime of 16. This is a classic problem. 16 is somewhere between 12 and 20. So we're going to go one data value above, one data value below. We're going to do a difference quotient and include the units, even though I don't think there's points for them in this problem. So one data value above puts us at 240 minus 200 over 20 minus 12. It can be reduced to 5, but it does not have to be reduced to 5. And again, there are no points for units, but go ahead and include the units just to be in the right habit of doing that. If you read the wrong units, in this case, you would not lose any points because there were no points for units. All right, let's go back to letter B. And in letter B, now we have using correct units. Explain the meaning of the definite integral from 0 to 40 absolute value of v of t. Well, because we have those absolute value around the velocity function, that's forcing the graph to be totally above the x-axis, so any area accumulation will be guaranteed to be the total distance traveled, not necessarily change in position and not displacement in this case. And then we're going to use a right-Riemann sum with 4 subintervals to approximate the value. And notice from the table above that the subintervals will not be equal. So let me erase. So when we break this into 4 subintervals, we have 1, 2, 3, 4 subintervals. We're doing a right sum, so this would be right endpoint number 1, or height number 1, height number 2, height number 3, and height number 4. And then we have a base of 12, a base of 8, a base of 4, and a base of 16, 24, 30, yeah, base of 16. So let's look at our work. First, for the interpretation. The definite integral represents the total distance Joanna jogs measured in meters from 0 to 40 minutes. That's really a pretty easy explanation. For the right Riemann sum, you do not have to set it up with the absolute value and the v of v of v of v of. But you do, in your work, you have to make sure that the 220 that was in the table is a negative, that you record as a positive, because that's doing the absolute value right there. And you may leave your answer just like that. There's no need to do any arithmetic or simplification. Notice they included the meters again, but if you have it in your explanation, which you should, you certainly don't have to record it again. You get 1 point for showing the right sum, and you get 1 point for the approximation, and these 2 points can be earned, both points can be earned right here. Going back to part C, now we introduce Bob, and Bob is riding on his bike along the same path, and his velocity, instead of being given as a table, is given as a function, a cubic function. And his velocity is also measured in meters per minute. We're looking for Bob's acceleration, which is the derivative of velocity. So this is a very simple power function, and we're going to take the derivative by the power rule, and we're going to substitute 5. So when we take the derivative of Bob's velocity, we get 3t squared minus 12t. Then you're going to substitute the 5. You can leave your answer just like, in fact, you don't even have to make 5 squared 25. You could have this just be 5 squared, and that would be a sufficient answer. Or, of course, simplifying it to 15 would give you the correct answer. 1 point for using b prime of t, and 1 point for the answer. And then lastly, in this problem, we're looking at the model from part, based on the model B, sorry, I got to read carefully. Based on the model B from part C, so in other words, we're focusing on Bob, find Bob's average value of velocity during 0 to 10. So this is going to be our 1 over b minus a from a to b. So we want the average value of the velocity function. In this case, 1 over 10 minus 0 from 0 to 10, accumulate area under velocity. And so you can see there's the 1/10, 0 to 10. This is a simple polynomial function, and so we can, or a power function, and we can find, or it's comprised of power functions. It's a polynomial function, and we can find the antiderivative reversing the power rule, substituting, and in this case, since this in the year 2015, this was not a calculator question, we would definitely want to leave our answer this way, or even more simpler than that. When I substitute the 10, I would have, instead of 10,000, 10 to the 4th. And that would suffice, and same thing here, 10 to the 3rd power times 2, 300 times 10, and that would suffice as my answer. I don't have to simplify. 1 point for the integral, so that is this portion right here. 1 point for the correct antiderivative, so that's saying that you use the reverse the power rule correctly, and then 1 point for your answer, simplified or unsimplified.